Here's the solution to questions 4 and 5 on the Chapter 5 quiz on web courses. And this deals with a block on a frictionless ramp that has a mass of 10 kilograms attached to a rope that goes over a pulley that is attached to a block that has a mass of 5 kilograms. So here we know there's no friction. And this angle is 40 degrees. And question 4 asks, what is the component of the weight down the ramp? And question 5 asks, what's the tension in the rope? So those are really just two parts of the same question. In order to get the tension in the rope, you have to calculate the component of the weight down the ramp. So we'll just treat this as the question of what is the tension in the rope, and we'll answer question 4 along the way. So to do this problem, basically what we're going to do is we're going to set up a free body diagram for each of these two objects. So for the 10 kilogram mass, there's its weight down. There's a normal force that is perpendicular to the surface, and those are the only two forces. There's no friction, so there's no other horizontal force acting on it. So these are the only two forces. Oh, I'm sorry. The tension, of course, of the rope. That's what we're looking for. The tension in the rope pulling it up the ramp. And if there were no rope, then the net forces of the weight and the normal force, the net force would be down the ramp, and it would slide down the ramp unimpeded. There's some tension from this thing. We don't know how big it is, so we don't yet know whether this thing slides down the ramp or slides up the ramp. So we'll have to figure that out. So what's the to get the tension, we're going to need to be solving for Newton's second law in this direction, in the direction along the ramp for this object. So this is the free body diagram for the 10 kilogram object. And that means we need to get the component of the weight that is in the direction of this axis along the ramp of the tension. So since the ramp is 40 degrees above the horizontal, that means that this tension is 40 degrees above the horizontal, and that means that the normal force is 40 degrees away from the vertical. And if that's 40, we're just sort of working our way around here. If that's 40 degrees, then this is 50 degrees. And this guy here is opposite this angle, so it's also 40, which means this one is 50. So why did I do all that? Because ultimately what I'm going for here is the component of the weight that is parallel to the ramp. That's this guy here. I'm going to call that Wx, and that Wx, based on how I've drawn this triangle, is either W cosine 50, that's also equal to W sine 40. And you may remember that in the book and in class we showed that the acceleration down a ramp is equal to G sine theta if theta is the angle of the ramp above the horizontal. So that would be our sine of 40 degrees. So the force, the component of the force down the ramp, is then just m times g sine theta, which is what this is. M times g is W times sine of the angle for this ramp, which is 40 degrees. So the answer to question 4, which is what's the component of the weight down the ramp, is just 10 times 9.8 times sine of 40, and that's 63 newtons. So the component of the total weight down the ramp, the component of the total weight, which is W, this is 10 kilograms times 9.8 meters per second squared, which is 98 newtons. The component of that force that happens to be pointing down the ramp, we work out to be 63 newtons. So now I can write Newton's second law for the 10 kilogram object, and I define plus x to be up the ramp. That's how I'm choosing my coordinate system. So then the sum of the forces in the x direction for the 10 kilogram object equal the mass of the 10 kilogram object times its acceleration. And what are those forces? If I define up to the right to be positive, then the tension is positive, minus 63 equals 10. That's its mass times its acceleration. So that's the equation of motion for the 10 kilogram object on the ramp. What about the 5 kilogram object? Well, it has two forces acting on it. Its weight down, W5 we'll call it, which is just 5 times 9.8 or 49 newtons, and it has a tension pointing up, which is the same as this tension because the rope is massless, the pulley has no friction and no mass, so the tension attached to the 5 kilogram object is the same as the tension attached to the 10 kilogram object. So those two things, I can write Newton's second law for this object. Now I'm going to decide here which way for this object is going to be up and which way I think this thing is moving. When I wrote positive ma here and a positive t here, that meant I was implicitly assuming that the acceleration is up the ramp for that object, and therefore it would be down for this 5 kilogram object. That may turn out to be the wrong guess. We're going to find out. But I'm going to guess that the acceleration is down, and the reason that's important is I need to make sure that every set of arrows that's going in the same direction has the same sign. So I'm going to guess that it's down. What happens if I'm wrong? I'm going to get a negative number for A. That would tell me that the thing is accelerating up. But let's do it. So what do we get? In this case then, I'm going to define down to be the positive direction for this object. So then I have 49, which is the down force, minus t equals 5 times A. So that's my equation of motion for the 5 kilogram object. Now all I have to do is combine these two things to solve for t, so that means I want to eliminate A. So algebraically, here's a quick way to do this. I've got 10A here equals something. This is 5A equals something. So this thing, if I just multiply this equation by 2, what do I get? 98 minus 2t equals 10A. So it's just a little shortcut that happens to work out because this is handily half the value of that, 5 half of 10. So I just double this equation, so this is still true. So now 10A equals this, but 10A also equals this, so that means this thing equals this thing. So that gives me t minus 63 equals 98 minus 2t, and that then gives me, rearranging, I put 2t over here, gives me 3t, I put the 63 over here, that gives me 98 plus 63, which is 161, and that then gives me t equals 161 over 3, or 53.7 newtons. Unfortunately, on web courses, the correct answer put in automatically in the system was the wrong answer, and so the automatic grading did not give credit for this correct answer. It gave correct credit for a wrong answer, namely 49. This is the correct solution to this problem, numbers 4 and 5, and that's how that works. If we wanted to figure out the acceleration, then we could easily do that because we've got the tension and we can figure out which way is the thing actually moving. And so if we wanted to do that, we would say, let's take a look here. I've got that the tension is 53.7 newtons. One of my equations was 49 minus t equals 5a. So that becomes 49 minus 53.7 is 5A, and 49 minus 53.7 is minus 4.7 equals 5A, which gives me A equals minus 4.7 divided by 5, or about minus 0.94 meters per second squared, and we do have a minus sign there. What does that mean? That means that, in fact, since I defined when I set up these equations, A is going down, and the definition that showed up mathematically by me giving the same sign to the acceleration term that I had given to the weight term, which is pointing down, I get a negative number. That means I guessed wrong, and the thing is actually accelerating up. So this block is sliding down and pulling this 5 kilogram block up with it. Okay, so we get the negative number. So it doesn't matter if we guess wrong. We just have to be consistent when we guess, and that consistency shows up with having the same sign for arrows that are pointing in the same direction. The weight of this thing is pointing down. I drew A pointing down. They're both positive here. If I had guessed correctly and drawn A going up, then the tension term and the MA term, the acceleration term, would have the same sign. It's also completely up to me to decide which one of those I make positive or negative. It doesn't really matter. I would just change the sign of all of these terms. But if I had put a minus sign here and a plus sign here and a minus sign here, but drawn things this way, that would be conflicting with what I had done for the 10 kilogram block, where I had assumed that A was up the hill and therefore had the same sign as the tension in that rope. So you have to be careful to be consistent with those things all the way through.